Hello friends, in this video we are going to discuss about a numerical on excess carrier concentration. In this numerical, it is given that consider a silicon sample at T equals to 300 K. That means the silicon is placed at room temperature 300 K with uniform donor concentration. And the donor concentration is given by Nd equals to 5 into 10 to the power 16 atoms per centimeter cube and is illuminated uniformly such that the optical generation rate, that is the G optical, is equals to 1.5 into 10 to the power 20 per centimeter cube per second. The incident radiation is turned off at T equals to 0. Assume low-level injection and ignore surface area. And it is also given the carrier lifetime of holes. Tau P0 is given by 0.1 microsecond and tau N0 is given by 0.5 microsecond. So find the hole concentration at T equals to 0 second and find hole concentration at T equals to 0.3 microsecond. So for the case 1, it is given that the donor concentration value in D is equals to 5 into 10 to the power per centimeter cube. And it is also given that is the generation rate due to the optical energy is equals to G optical 1.5 into 10 to the power 20 per centimeter cube per second. Now the light has been turned off at T equals to 0, assuming the low level injection, and if we ignore the surface effect, then we can say that this G optical will be equals to del P divided by tau P0, where del P is the excess carrier concentration and tau P0 is the excess carrier lifetime. So we can say that it will be equals to del P will be equals to tau P0 into G optical. So tau P0 is given by 0.1 microsecond and G optical is given by 1.5 into 10 to the power 20 per centimeter cube per second. From this data, we can find, if we calculate this, then we can find it as 0.15 into 10 to the power 14 per centimeter. So this is the excess carrier concentration that we have found, del P. Now, if we want to find the value of hole concentration at T equals to 0, then we can say from the equation P of T equals to P0 plus del P e to the power minus T by tau P0. So from this equation, if I put T equals to 0, then we can find the value of P at T equals to 0. So it will be P0 plus del P e to the power minus T tau P0. Now, we know the value of del P. If we know the value of del P, then we can put the value of del P. So del P can be written as P0 plus 0.15 into 10 to the power 14 e to the power minus the value of t is 0, so tau p0. So you can write p0 plus 0.515 into 10 to the power 14 into 1. Now we can say that the value of p at t equals to 0. So at t equals to 0, the light has been turned off. From this equation, we can find that p at t equals to 0 will be equals to p0 plus 0.15 into 10 to the power 14. But this p0 value has not been given in the above question, so we can take it as 0. So ultimately the whole concentration will be 0.15 into 10 to the power 14 per centimeter. So this is the value of the whole concentration at t equals to 0. Now in the question B, we have to find the value of whole concentration, that is P, at t equals to zero point 0.3 microsecond. So for that case, P0 plus del P into e to the power minus 0.3 microsecond divided by, and the tau P0 value has been given as 0.1 microsecond. So from this equation we can find the value. My P0 value is 0 and del P value, we have already calculated del P value, that is 0.15 into 10 to the power 14 into e to the power minus zero point 0.3 divided by 0.1. So from this equation I can find the value. So if we do the calculation, we will get 7.46 into 10 to the power 11 per centimeter cube. This is the value of the whole concentration at t equals to 0.3 microsecond. So in this way, we can calculate the whole concentration at different instant of time when the light will incident on the semiconductor. Thank you.